All right, so let's get started. Uh, if I seem a little out of it, it's because I feel pretty sick right now. I may not, well, I don't know. I see I'm smiling, but I don't, don't really feel like smiling right now. But that's okay. I woke up with some kind of bug, so my head hurts and my joints all hurt. But anyway, we'll do physics, and that'll make us feel better. I hope. Anyway, I got a problem here, kinematics problem. Rocket is launched from a launch pad that is 7 meters above the ground. The rocket has an initial velocity of 12 meters per second at launch and is accelerating at a constant 12.2 meters per second squared upwards. Find the time it would take for the rocket to reach 80 kilometers of altitude above the Earth. So, you have this problem, and you got a couple things you could do to help yourself out with it. I mean, drawing a picture isn't a bad idea, all right? I mean, you don't need a pretty rocket, but you might think about like certain parameters, right? You might say, okay, here's my rocket. Wow, look how pretty it is, right? That's my rocket. Okay, and when it starts, if you think about it, it has already a displacement above the Earth, right, of 7 meters. So that little detail, right, that itty bitty little detail might matter. In the grand scheme of this problem, it's probably not going to make a humongous difference, but it does matter. It will affect the answer. It does mean this rocket takes less time to get to that altitude. It already started 7 meters above, right? So you have to account for that, right? That's an initial displacement, specifically an initial vertical displacement, right? This problem we're assuming is just up. Okay, it's unidimensional. Could you do two-dimensional problems like this? You can, right? When we get to like cannonballs being fired, right? They're going up and they're going out, right? Then we need to account for those. But for this problem, you say, oh, it's unidimensional. It's a little bit easier. All right. So what I might do is I might list out what variables I have, right? So I have like an initial velocity. I can call that vi. Okay, technically VIY, right? But this is all on the y-axis, so if you don't want to, you don't have to. But its initial velocity is 12 meters per second. Oops, 12 meters per second. We have, as we just said, an initial displacement. So SI, technically y, is positive 7 meters. We have an an acceleration. So we have acceleration in the y. It's constant, and if you're a clever cat, you might be saying, should we take into account gravity here? It should be a little bit clearer. I mean, I wrote this, and I'm reading it, and I'm like, well, it says it's accelerating at that rate, which would imply to me, the way I'm writing this, at least the way I want it to read, is that that's what it's experiencing, which means we've taken into account gravity already. Does that make sense? Meaning, like, you might say, shouldn't we subtract the 9.8 since it's going to? That's a very good thought. If you're thinking that, that's a good thing. But in this situation, we're saying, no, we already took that into account, right? That's the kind of thing you'd probably want to ask if you weren't sure. You're like, hey, does that take into account gravity? And it's a good thought to have. It means you're thinking about, what are the forces acting on this, right? So that's good. We're assuming there's no air resistance, okay? With gravity, I mean, you might say, well, isn't there gravity? Again, we're taking that into account. So that 12.2 means we've already accounted for that negative 9.81. Okay, at least that's the way I'm writing this. All right, could you have a problem where it says the motor is attempting to cause this much acceleration? Yes, and then you might say, maybe I should take into account that 9.81 down. All right, but in this case, no. If it was forces, if it said the rocket is being supplied this much force up, then you would definitely want to take into account gravity. Okay, but if we've already included acceleration, you can make the assumption that that's been taken care of. All right, I'm just saying that because to me, you always want to make sure you're not, you have the correct premise, you have the correct starting point for this problem. Okay, so hopefully you're not like, oh my God, it's confusing. I just want to make sure you're aware that these problems can be harder, right? So this is 12.2. It's positive because it's going up. Presumably the rocket wants to go up and not down. Okay, at least not right now. And what else? We are looking for what? Or rather, we have 80 kilometers. That's our final displacement. So I could call that my SFY, my final displacement in the y, okay? And that's 80 kilometers. And hopefully you're saying, kilometers, I'm going to have to convert that. Exactly. And if you convert that, metric system is great. You just multiply it by 1,000 in this case for 80,000 meters. If you're like, hey, I still don't know how to do that, you really got to make sure you practice those conversions. They're very important. Okay, this video, I'm trying to keep it relatively short, so I'm not going to show it. But by all means, comment or ask, right? I'm happy to help. Okay, so this is converted to meters because, again, we need units to cancel. Yay. Okay, and then you say, what equation, or rather, what am I looking for? The problem says find the time. So I'm probably looking for t. How much time? Okay, and hopefully you're looking at this and saying, I know exactly what equation to use. And that equation is our very nifty kinematics equation. I don't really know. I mean, if it has a name, its name is Steve. Its name is Ralph. I don't really know if there's a specific name. I would probably call this like a universal or constant acceleration in one dimension, I guess. There's probably a name for it. I don't really, does it really matter? No, that's not the point, right? The equation, of course. And if you say, well, doesn't it? Because if I need to describe it, well, yeah, you need to know what variables you need, right? At the end of the day, I don't care if the name is Steve, Ralph, or Bob. What matters is, do you know why you're using Steve or why you're using Bob? And if your answer is no, then it doesn't matter what the name is. You see what I'm saying? Like, it doesn't matter, okay? At least I don't think it does. Maybe people will disagree. In any case, our equation is that 1/2, I'm going to try to write this out nice and neat, 1/2 AT squared plus VIT plus SI plus SI equals SF. And remember, S is kind of a weird one. And if you look up this equation online, if you type in kinematics equations, it's not usually written with S, which is kind of annoying because S is the label for displacement, so they should be consistent. But they often use like delta X, the change in X, right? That would be in the X-axis. What about the Y-axis, right? I mean, that's why S is better. At least it's consistent, okay? Do you have to use those symbols? No, but it's probably better to be consistent. And use this equation. Why? Because you're like, hey, I have a initial velocity. Hey, I have an acceleration. Hey, I have a displacement. Oh, I probably use this equation. Okay. Even if you didn't have initial velocity, if the initial velocity was 0, you would still use this equation. Okay. So very versatile equation, very useful equation. And you say, what do I have? What can I plug in? I'm trying to find t. Okay, so t is my unknown. So I can plug my numbers in. I think it's probably easy for me to just type it, especially with the units. So I'll just do that. Let me show you that. So we're typing in, we have what, 1/2. And I'm going to write 1/2 as 0.5, just a little bit easier to write. 1/2. What I might do, by the way, is especially for physics, I might start to use LaTeX, which is a program. It's a markup language, which is a fancy way of saying it makes this look a lot neater. Okay, because doing this in Paint is not great. All right. If I can get a LaTeX editor, I can do this in real time and make it look a little bit prettier, but it is what it is. So 1/2 is 0.5. Acceleration is positive 12.2 meters per second squared. I'll put that in parentheses just so we're on the same page, right? Times t squared. We don't know t, right? We don't know what t squared is, so we leave it as t squared. And this is then added to VI. VI in this case is 12, so 12 meters per second. And this is multiplied by time, which again, we don't know, is equal to, or I'm sorry, plus, I'm always forgetting, plus SI. SI is 7 meters, right? Very small amount, but it matters, okay? And this is equal now to the final displacement. Where is the final place I want to be? 80,000 meters in the air from the ground. If it was from the launch pad, right? If it was from the launch pad, then it would just be what? A displacement total of 79,993, okay? You got to think about this as we've already gone 7, if that makes sense. Like the rocket started here, which means we only really are concerned with this displacement, okay? At the end of the day, displacement is a vector. It's from a fixed point, so I need to use the 80,000 and I need to use the 7. But mathematically, what it ends up doing is treating it as if we're only going 79,993. Okay, so you should hopefully be able to make sense of what I just said, meaning hopefully you're saying, oh, I see. You could think of it 2 ways, because that's very helpful, especially in physics, is to think, okay, I can approach it from this angle or I can approach it from this other angle, and hopefully by approaching it from both angles, you get to see the whole thing. Okay, like, I mean, I'm going to give you a silly analogy. Looking at playing cards, looking at one side tells you a little bit. Okay, these are playing cards. The other side tells you, it's a 2 of diamonds, right? I don't know. Does that analogy make sense? I don't know. I think it does. Anyway, and we do this thing called algebra. Okay, first thing I would do is get rid of the 7. Okay, and if you do this, somebody might be saying, "Oh, come on, you can't just come on. You're making a mistake here." Well, let me just prove a point to you, right? You say, "Okay, I'm going to do an algebra. I'm going to do an algebraic. I'm going to get rid of that 7 first." You subtract 7 from both sides, and you get, to be fancy, I'm going to just copy this to save myself some time, right? Because that's smart, right? So I'll take that and I will copy that. and then I subtracted 7 from both sides. Now I have that 79,000. Oh my God, what happened? What happened? Oh boy, 79,993, I believe, if my math is right. Okay, meters. Hey, can you subtract meters from meters? Absolutely, you can. Okay, so make sure the units check out. If it was kilometers and meters, then you can. Right, so be careful. And you might be looking at this and saying, okay, I got t squared and I got t. Uh-oh. Yeah, uh-oh is right. If you really want to be a fanatic and try to factor this, be my guest. I would not recommend that. Okay. You say, can I complete the square? I guess you could. Or you could use the quadratic formula. That would be my recommendation. I would say, hey, that's probably working smarter, not harder, right? So, to do the quadratic formula, recall you have ax squared plus bx plus c is equal to 0. Okay, that has to be true. And when I say has to be, I don't mean like, oh, it's recommended. I mean, if it's not, the quadratic formula doesn't work. Or it works, but you're going to get the wrong answer. Okay? And so what this means is that I need to get this equal to 0. All right? And if you're a clever cat, is there a way to make the quadratic formula work for any c value? Or for any equals y value? As in, like, could it be 79,009? Yeah, you could. But you can't use the quadratic formula that's commonly given. You need to add a y term into it, okay? Which isn't that hard, but there's no reason to reinvent the wheel, if you get what I'm saying. So we do the quadratic formula. You got to identify, first and foremost, what a, b, and c is, and you better make sure it's equal to 0. So I better make sure that I make this equal to 0, and the easy way to do this, of course, is just to subtract the 79,993. And that's why I'm saying somebody might have been like, wait, just subtract 80,000 first. Yeah, exactly, and you get the same answer no matter what, right? So what does that look like? This minus 79,993. And it's negative, and that matters big time. So don't make a mistake and make it positive, because then it doesn't work. This will not work. You'll get a wrong answer. Okay? So equals 0. And now I can cook, so I can put in my A, my B, and my C. Be very careful, because A, you're tempted to say, oh, and it's funny too, because A happens to be the A term. You might say, oh, it's 12.2. You gotta first half it. Or you could do some algebra and get rid of the half, but then your B term gets doubled. And I would advise you just to half the A term. Okay? I mean, could you double the B term? Yeah, you could. You get the same answer, but there's no reason to do that, I would argue. It's the same answer either way. Halving A makes sense. So rewriting this, what does it look like? Half of 12.2 is, 6.1, right? 6.1 is 12.2 divided by 2, I believe, unless I'm losing my mind, which today feels like it. Minus 79,993 meters equals 0. Okay, and then I can plug it into the quadratic formula. We go to Desmos. Yeah. And we go into Desmos, and we, just so you can see it, it's just easier, right? You can use your calculator, of course. And we have the quadratic is negative b plus minus, oh boy, do I know how to do plus minus in this? I don't remember. Does it have it here? Let me see. I think it does. Let me get rid of this. Hang on. No, go away. Yeah. Yeah, go away. Plus minus, where are you? Where are you? Really? They don't have it? Or unless it's right in front of me and I'm somehow missing it. They got inequalities, they got square roots, they don't have, wait, maybe, no. Okay, well, then we do it this way, ready? Plus minus sign. And I could probably just copy this. Or, ready, I'll be fancy. Ready for this? Let's do this. Plus minus alt code. Ooh, fancy. The alt code is alt241. Okay, so what does this mean? It means if you're in Windows, which I am, I can type those letters, those numbers I should say, and it'll put it in for me. It's pretty nice. Let's see if it works. Alt241. Let's see. Alt241. I say it's nice, and then of course it doesn't want to work. Alt241. Maybe it's Alt2. Sometimes they put 0 in front. Alt0241. Well, it's not working. All right. Well, I was going to be fancy, and then I can't be fancy. Okay. Yeah, we'll try this, actually. Alt0177. Maybe it's that. Maybe they changed it. I don't know. Alt0177. Everyone's watching this being like, what a hack. He can't make it work. Yeah, it should work. I don't know why it's not working. So I can hopefully just copy this, and that should work. And we go here, and we click here, and hey, there it goes. Good. It's kind of funny that Desmos thinks that that's a variable, but whatever. Okay, hopefully that works then. The equation then plus minus, and then we have what? Square root. We got b squared. We got minus 4ac, and this is all over, I got to be very careful. See, that would be incorrect. I got to put this in parentheses. Otherwise, we got problems. Divided by 2a. Okay. Now, the plus minus symbol, believe it or not, mathematically means I have to do it 2 times, right? Hopefully, you're like, yeah, I know that. So let's start with maybe the plus. So I did all this work for no reason, right? And the nice thing about Desmos is I could say, hey, give me numbers. So then let's see, my A was what, 6.1? 6.1. My B was 12, I think. Yeah, 12. Cool. So that's 12. And then C, very importantly, is negative. Oh, I put C as this. Oopsie daisy. Sorry. Negative 79,993. Very important that it's negative. Very, very, very important. Otherwise, it won't work. And then A, we set with 6.1. Sorry about that. And you're going to get one solution to the quadratic. Let's see if it pops up. Yeah, 113.535. Okay. Does it make sense? Well, that means 113 seconds, roughly, 113.5. Okay, so that's about 2 minutes. And assuming, I just picked some numbers, right? I didn't I'm not a rocket scientist, believe it or not. I may have the hair of a rocket scientist, but I don't have the brain of a rocket scientist. It's pretty hard stuff. But yeah, you're like, okay, about 2 minutes, roughly. Oh, that's pretty believable, actually. That's actually quite, for the numbers I picked, I'm pretty happy about that. Maybe a rocket scientist is like, no, not at all, but I think it's pretty close. I don't know. And then, of course, we should do the -1. So this is one of your roots. Remember, this is where the parabola would cross the x-axis, right? So that's where it's, y equals 0, right? The x-intercept. So then I can do my minus, and more than likely, as I expected, when you do one root, usually positive, one root, usually negative. Not always, but usually. What does this mean? Well, in theory, there are 2 times in which this was true. Because parabolas are, right, if it's a positive parabola, it has like a U shape, right? That U shape, we really only care about 1/2 of it, what's called a branch, okay? And if you're going, what is a branch? What do you mean by a branch? Just a quick little thing. If I type in tangent of x and I plot it, you'll see tangent has what appears to be many, many, many graphs, right? Tangent has a vertical asymptote, 2 vertical asymptotes. It shoots up to positive infinity and it shoots down to negative infinity, okay? Tangent is sine over cosine. As sine of x approaches 1, okay, your sine value, your y value, approaches 1. And your cosine value correspondingly approaches 0, which means 1 divided by 0 effectively. And for those taking pre-calculus or calculus, you're like, oh, a limit. Exactly. The limit as x approaches 1 would be positive infinity. And then as it approaches a 0, okay, we touch 0. You can see that because that's when cosine is equal to 1, sine is equal to 0. And then what happens? When you get to -1, right, we approach negative infinity, okay, because then sine returns -1. Okay. Anyway, my point is this graph is non-continuous. You'd have to pick a branch. You'd have to say, this one, right? This one right here. Same thing with the parabola, except you would, it's not as complex as this. You would say, I only care about this portion. I care about the positive portion because I can't really have negative time. Technically speaking, you could get into some problems where maybe you could use that, right, if you model it that way. But generally speaking, we throw out the negative root, generally, okay? And I'm not saying never, and I'm not saying it's never going to happen. I'm just saying it's like usually you're going to say the negative root doesn't really make sense. Ask yourself, does it make sense? It means if I go back in time, about 2 minutes before launch, you're telling me that this thing was up in the air. That's what you're saying. Well, that's not what the rocket was, right? Could you have something that follows that behavior? Absolutely. If I have something that's like imagine like a skateboarder going up and down a half pipe. Yeah, then I could say, hey, where was he? If I make this the starting point, the middle of the half pipe, then yeah, 5 seconds ago he was here. 5 seconds later he's here. 10 seconds he's here. 15 seconds, right? You see what I'm saying, right? But again, that's kind of a special thing, okay? And again, I hopefully am making sense. Hopefully you're saying, oh, cool. Hopefully you're not going, what in the world is going on with this tangent stuff? We don't need it. I'm just using it as an example. Okay, so anyway, you got your answer, 115, because we don't really care about the negative. We care about the positive. 113.535. I'd probably round that to 113.535 to the thousandth place, okay, which is pretty good. This answer is okay, right? I mean, it's not that crazy. If I say 115 seconds, you're like, oh, okay. Maybe you want to convert to minutes, right? You would divide this by 60 and get about 2 minutes. It's like probably 1.9 or something like that, right? But I think saying this time is perfectly reasonable, okay? So hopefully you're looking back at this problem and you're saying it looks good. How could you check your work? The beautiful thing about math is you can always check your work, okay? Which means if I were to plug in that time, okay, and then say, what's my SF? I should get out 80,000. Okay, so let's just do it, right? Like you're saying, okay, I guess. Well, let's check it, right? So if I do that, we go back to Desmos, maybe. We go back to Desmos, and let's make the graph, right? And as a matter of fact, just to prove a point to you, right, the quadratic formula is great, right? Nice thing. You could always graph this and be clever, aka, here's my function, 0.5 times a, we said was 12.2, right? We still have the half, so we're back to that. Times, we just said, what was it, 113 point, oh boy, what did I say, 535, I think? It's going to be close, okay? I square that, that's a time. I add, I should have wrote this down, right? 12 times 113, this is the time, right? We just found it, 0.535, I think. Again, maybe you're like, come on, you just said it. I know, I forgot, sorry. Plus 7, and you can already see, if you're like, wow, look at that. Plus 7, wow, that's insanely close. And you might say, how come it's not perfect? Number one, I might have remembered it wrong. It might have been 113.525. It might have been 545. It might have been whatever. The other reason is this. Even if I did remember correctly, I rounded it. I took off some of its precision, right? Which means I'm going to, in theory, lose a little bit of precision. Okay, this is pretty darn close. Okay, the probability of me happening to get like I happen to get I guess the answer is very low. Okay, very, very, very low. Okay, so hopefully you're like, I see. Now, I said with graphing, if you're clever, because if I zoom out, let's see, will this work for me? Oh, I suppose I need to put in the variables, right? That would be a better idea. So if I were to graph this, so just prove a point. So that's the answer. Good, right? If I plug in x squared, and then I change the time to x. And again, you might say, it wasn't a t. Well, it doesn't make a difference. I can make it t, I can make it x, I can make it a, I can make it b. I can make it a smiley face if I really wanted to. Don't do that, though. Okay? This is the equation written out in general terms, right? So now I have solving for t, or rather plugging in t, getting a displacement. If you zoom in, here's your parabola. Better really zoom to see it. There it is. There's my parabola. Hey, it started where? Above the ground, right? How far above? 7. Pretty cool, right? Because when x equals 0, when time is 0, this, of course, is 7, right? So at time equals 0, we are at 7. Okay, that's good, right? And then what I can do, to be a clever cat, I'm going to zoom out a little bit, and I'm going to say y equals 80,000. And what I've done is basically said, hey, when do I reach this altitude? If you think about it, what I'm basically doing is visualizing this function. I know it looks like a line. That's simply because we are zoomed in big time, okay? You can see there it is with the parabola. If I go up to 80,000, which is the displacement I'm looking for, the intersection of those lines is essentially what we're doing with this equation. And if you look, you can see right there. Hey, I was right. It is 0.535. Look at that. 113.535. So again, hopefully you're saying, I get it. Math has consequences. Hopefully you're saying, I get it. Math is really useful. If you're like me in high school, you would have been like, oh, I don't like math at all. Because the way it was explained to me, I didn't like it. Okay, I like it now. I took calculus and I went, ooh, I like this. And again, that negative answer is not going to work here. We're not concerned about the rocket being up in the air to start and coming back down. I suppose with Starlink, or not Starlink, SpaceX, right, the Elon Musk company, I guess they do, right, but not before the launch, right? It's after the launch, right? Anyway. All right, so hopefully it makes sense. Hopefully you say, oh, I got an answer. Cool, okay? Unidimensional. It can get way more complex. I'll try to put another video up here soon. Probably not today. I'll see what I can do. And going over some more complex ones. Okay, but hopefully this got you started. Hopefully you're saying, yeah, that ain't that bad. All right, have a great rest of your day.